All right. We're going to have a lot of fun today. We're going to have a lot of fun in this, this session. We're going to keep it very engaging, and which means that you need to step up and ask questions and challenge the speakers, challenge me. The way we're going to run this is the first 10 minutes I'll speak, and I'll tell you a little bit about my perspective on this. It's about 10 years since I started working on this, in this area, and I want to sort of share that with you. A few of you may have heard this before because I actually had a little workshop last week and I said the same thing. So for you guys, just focus on your work for now. But anyway, so 10 minutes I'll speak, and then we'll give 20 minutes to each speaker. That takes, and there are 4 speakers. That takes us up to 1 hour, 30 minutes. But we will not end there. The way everything is set up, we actually do have a half-hour budget buffer. And I'm going to use that to have a discussion with all the speakers. I'll ask them some questions. I expect you should ask them some questions, and we'll make it interactive. And there are 5 seats here, or 6, what is it? Yeah. So there's 1 extra, and so we have a surprise guest. You know who you are. You're here already. Okay. With that, let me begin. All right, this session, for those of you who is on Intelligent Edge, so if, like they say in the planes, if you're not on the right flight, you probably want to go. Okay, that joke didn't work, sorry. Okay. So I'm going to say a few things about my own personal journey on this. So before I say, this has been hammered into you, I think, by now, but I want to take this time to do it as well. Microsoft Azure is large. It's very, very big. It's very complex. Serving, as these numbers sort of indicate, there are so many moving parts. The network is massive, 33,000 plus miles of lit fiber across our WANs, more than 100,000 miles of fiber inside our data centers, millions of components, millions of servers, all interconnected, packets flowing from one point to another point. It's an engineering marvel in some sense. It's planet scale, it's huge, and as you think about research, you can start to see that we need discipline, a lot of discipline in designing such systems. And we have to be very careful, because if anybody is going to take dependency on us, on the cloud, we better damn well stay up all the time, right? That's why people work very hard and they worry about anything breaking at any given point anywhere. So it's a large system. In terms of the economics of it, you also heard Mark talk a little bit about it. I had these numbers too, so I want to share them with you as well. In FY18, $23 billion revenue. That's a significant amount, and it's going fast up, 89% growth. But I have, these numbers are from my F17. I wanted to update it this morning, but I couldn't. But you can sort of see the numbers, how fast the growth is happening. We can't build fast enough. That's the deal. There's so many customers, we can't build fast enough. In fact, we have to slow down to avoid overpromising. But from a research, that actually makes an interesting problem too. I mean, if the cloud could be statistically multiplexed, we could actually use these servers again. So there's a lot of researchers in Microsoft and my group and close-by groups that do that. And so you can also see from this number, 90% of the biggest, largest companies in the world depend on it. So it's all good. So that sort of sets the stage for things. All right. So how did this thing start for me? In 2000... have the right date? Yeah. In 2008, I invited Satya from CMU, many of you might know him, to come to Microsoft Research in Building 99. And we had a one-day brainstorming session on what does it mean to, what is going to happen after cloud? Things change too. In fact, I would challenge you to think like that too. 20 years from now, what is the world going to look like, right? So that's kind of sort of what we were talking about. And then out of that discussion came out this paper. This is the paper that people cite as cloudlets. And we published this paper. Initial thoughts, you look back at it, you sort of think, okay, well, we could do things a little differently. Then this is the first article that came out on December 13, 2009. where it says how the cloudlet will beat the cloud. This is the edge. So think of it as the edge, the intelligent edge. And if you look at the citation count, which I just did a little while ago, you can see a paper is very heavily cited. So a lot of people have read it, are working on it, and are publishing on it. Now, in the faculty summit of 2009, I did a demo of edge networking. And the demo was the actual, what is now the Skype translator. We literally, I was sitting here, Eduardo was with me, and we offloaded this translation capability to the edge on a phone, and then he was talking in Spanish, I was talking in English, and we were doing this in real time. And then we published the paper for the programming model for that, of how programmers will do that, and that too has been cited quite a bit since then. Okay. So then I had this opportunity. We have in Microsoft Research, we have this thing called the DTR, or Disruptive Technology Review, where researchers can go every year. It happens every year. Now it's starting to happen every 2 years. But can sort of go and talk to the CEO and the entire SLT. They come into the Building 99 and tell them about what trends or what things we think can either disrupt us or we can do to disrupt the industry. And so in that, I actually presented this. I presented this. If you look at this picture, you will sort of see this called Maui Node. That's the paper that I was referring to. But really, this is kind of the edge, right? And this is the cloud. And one of the things I said at that thing, the slide is from that time, was that, hey, you have these wireless things, you have access points, you've got the switches, and here, right next to the switch, is your edge node. That was the Maui Node. And then, we talked about it. But I made a mistake. Steve Ballmer, who was the CEO, asked me, okay, Victor, what do you think we should do differently today? Right? He didn't ask me about the future. He asked me, what do you want me to do today? And that was a question I did not expect. It's a shame on me now. I look back at my life and think that was shame. But think about it. As researchers, we always focused, right? We're always saying, oh, we can do this, we can do this. But here's the CEO asking me, what do you want me to change right now? And I stumbled a little bit, and I told him speech recognition, I think I said, or speech translation or something. And there was an EVP there, and he didn't buy into it. He said, nah, not needed. And in some sense, he's right. We have all this stuff going in the cloud, and it works. But so that was sort of didn't really work. So I went back, and I kept working on this stuff. I really believed it. And then I had another chance. In 2014, actually it was for 2013, but we did it in 2014. I had another chance in front of the SLT, but this time I took the problem on differently. I wanted to make the case that, look, in the cloud, we sell storage and we sell compute. I want to sell latency. Okay, latency is the hard thing because you don't have control many of it. You don't control the internet. So then logically, you will immediately say, well, one thing is to make many data centers around the world. The other, and that's not financially viable. So the other is, hey, let's put lots of edges around the world, right? So that was the thing. And I showed in this video, which I want to show you. I do have a point after all this, so let's spare me for a second. So I want you to watch this video carefully and tell me what you see. So there are 7 people walking. There's a camera that's taking this. This is the original video, right? Now we're going to do face recognition on it with 2 to 5 millisecond latency on the edge. And you should see that. And then we're going to run the same program. This is 4 years ago, right? So things are better now. With 7585. And the reason we used 7585 was because LTE, rule of thumb, is about 70 millisecond latency. What did you see different in the two? Can anybody, people who have seen it, don't please say, but did anybody see anything different in this? Come on. It wasn't? Okay, that's an observation. Anybody else? Would you like me to play it again? Yeah? Oh. Yeah, that's true too. I'll do it one more time. I want you to watch. So there's the original video. Then there is a video with face recognition when you're offloading 5 milliseconds away, 10 minutes, and then there's 75 milliseconds away afterwards. So that's the first one. And now here's the second one with the LTE latencies. Did you see this before? That's exactly right. There were 7 people, 7 were recognized. In the second case, there were only 4. That's a serious problem. That's a functionality problem. Imagine that something like that somebody else does, and you're actually losing serious functionality there. You can't do it. The system can't do it, right? It's not fast enough. So this is what I showed. I actually showed a bunch of other things too, but I'll show you another one, which actually may catch on. This is gaming, fast action gaming that was happening. And so Eduardo, you know, so he's playing this game. He's a top-notch gamer, and he plays the games with 5-second, 30-millisecond latency, and 40-millisecond latency. Now, in this particular video, all you're seeing is, I'll just point out because we really run out of time here, is really when he clicks, there's a lag, right, between the click and what he sees. So now if you translate this to a sort of a more serious game where he's fighting somebody and he's shooting, what you see is that as we increase the latency, he goes from killing everybody and winning the game to a point where he gets shot all the time because he reacts, but his reaction time is slow and the game is still playing, and boom, he loses the game. So that's not going to work. So if you do, say, cloud gaming, you know, it's not going to work unless you match the latency. So I'm going to just move forward. So I made this prediction after that in the DTR. I said the world is now moving in this direction. Okay, so you got these mega clouds. You got to have a disaggregated cloud. You're not going to be able to sustain mega clouds for various reasons. And it was sort of, the prediction was made by 2020, everything's going to look very different. All right, and I was actually, when I'd made this talk, I had actually gone through many examples of what are the different advantages of edge. Right, you can read this. I'm not going to belabor the point because you're going to hear more from people here. But this was not just a prediction made. This was systems built, showed this was happening. So what happened after that meeting is, this is just before Satya became the CEO. Steve Palmer asked me how much it's going to cost. And Satya, who was in the audience, said $380 million for us to do this. And Steve said, do it. I'm like shocked. I won. Well, not really. It's one thing to get senior management to agree. It's another thing to get the people who actually do the stuff to agree. And that's where everything gets stopped. So in the meantime, the world was kind of evolving too. I mean, Satya had gone and created his own. If you go, he has done tremendous work since then. He's a true believer there. And then I had seen the world sort of move in all the different directions as well. A lot of this conference was created. I was part of that. The FOG consortium was created. By the way, I hate the word FOG, and I also think they ripped off many of the things we did. I just called it FOG, but that's okay. And I actually have proof for that, but that's not. So then, but I was still not happy because where's the money? Where's the money? We needed a killer app. So then we had this observation. I was actually in sabbatical when this observation happened, that there are cameras everywhere. There are millions of cameras everywhere. They're streaming video. Nobody's looking at that. Computer vision and AI were becoming big. Systems were good. So then we started working. For 4 years, we have worked on video analytics, trying to show. And yes, I still believe there's a lot of money here, and I still believe this is the edge story from my perspective. And we did some good stuff here. We actually won 2 national awards because of the work we did here. Then something interesting happened. I was doing this work, I'm in Microsoft talking to all my colleagues. And then in December of, 2016, this guy, he's a VC, if you don't know him. He's a well-known VC from Silicon Valley. He gave a talk entitled The Death of Cloud. In that talk, he basically made the point for intelligent edge. He talked about AI. He talked about, doing the latency thing. Pretty much very, very similar to what we had been sort of talking about here. But it was outside. It was in the VC. He was he funds companies and things of that nature. Boom! It became a big thing. In the meantime, I have great respect for our CEO, and the reason I have a lot of respect for Satya is, well, first he has empathy, and I like that. But another thing is he's a smart guy. He has his finger on the pulse of what is happening in the world, and he watches it, he observes it, he talks to it, and then he makes decisions, right? So he's along, he knows we are doing this, but then he starts to see this, and then he goes out there and says, intelligent edge, we are all in. Microsoft is all into intelligent edge. It's not just the cloud story, it's the intelligent edge story. Now things start to move in a really, really big way. So this is what he says in Bill 2017. But he had started saying this already, as you can imagine. In the meantime, a lot of research reports start to come up. Hey, Edge is it. Edge is going to be the thing. And this is just one example of one of those reports. There are many who came up about how the Edge will eat the cloud. I actually don't believe that at all. And we will bring that up in the panel. And then, of course, you start to see news articles. You start to see people getting excited. There are so many. I just sort of put some samples here just to say that, all these, it was becoming a big thing. All right. Then another big thing happened. So Microsoft announces that we're going to invest $5 billion in IoT. And in the text, it talks about the intelligent edge as one of the key components to the $5 billion investment. Now things are hot, really hot. You've got a $110 billion company saying that we're going to start investing in this. That's significant. Now people are starting to move pretty hard. You're going to start hearing Ajman is one of our speakers, and he's going to fill in a lot of the gaps that I'm leaving here. But I'm just talking about it from my perspective of how exciting things are getting for me. Then a couple days ago, I was a PC chair of this symposium on edge computing. I'm sitting there and listening to the papers. We had all these paper discussion to figure out which papers to accept. I start to see papers in all these different areas, but edge-related papers. This is really exciting now. So you've got businesses starting to say, this is big. You got the VC community saying, we are ready to invest. You got researchers pointing out all the different issues, which is going to keep them alive, working for several years. And these problems and their solutions are quite innovative if you think about it. You have something now. It is no longer a fad. There's nothing of that. This is something very concrete because these problems will get solved. For example, one of the problems that still exists is availability and SLAs. In clouds, we have SLAs. So if you depend on something, you say it'll be there. When you introduce edge, what's the SLA? What's the availability? A lot of papers on that area, right? And since it's early work, there were all these holes, so we didn't accept all of them, but you can sort of start to see this. You saw things of like management. When you imagine that you've got not just one edge, now you've got tens of thousands of edge, way more than the cloud. How are you going to manage this? Who's going to own the edge? Is it going to be like the companies like Microsoft, or is it going to be sort of a federated model where somebody else owns the edge? We don't know. So as you think about all this stuff, you think, what about privacy? What about security? In cloud, we can offer you some level of security because we kept everything in lock and key. Now the edge is sitting on your premise. Somebody can come, take out the disk, copy it, put it back. Who knows what happened, right? Real serious problems come on. So my final thoughts here are there is a paradigm shift that is happening, and it is going to be very big, I predict. I just looked at some report, and it says this year is the year of AI on edge. I didn't focus too much on the intelligent part of it. I'll leave the speakers to do. And with that, we start this. Thank you. And then we will start the thing by having 4 speakers. I'm really excited to have them. Is Mang here? Yeah. Come on over. We're going to speak in this order. So let me introduce you to Mang. He is, many of you might know him. He was actually the director and investor of the Edge Lab in Princeton.
Well, thank you, Victor, very much. What a pleasure to be here. Thanks for the invitation. As Victor said, that my day job is the Dean of College of Engineering at Purdue now since a year ago. But then my nighttime and vacation and weekend is research in networking and continue to do that. Part of that is still a visiting appointment to direct the Edge Lab at Princeton, and the other is participating in the Open Fall Consortium. Victor and I, we have debates about the use of English words like fog or edge, and I'm going to just brush that aside for the next 15 minutes here. Since I lost 5 minutes trying to get Mac and Microsoft to work together, I'll try to be brief here. And the main message is on network decomposition. What is that? Well, the job, like the CEO's job, you've got a great one, and Victor, is to sort of decide who does what, at what time scale, and how to glue them back together. So it's not just allocating the resources, but also allocating the functions. And how each function is carried out is less of a concern for the decomposition itself. Now, there's the vertical decomposition, layering as a fundamental concept in networking to modularize a complex interacting system. And layering can be mathematically understood as optimization decomposition, both reverse engineering and also design synthesis for engineering. And for example, Kumar was the one who gave me and many in the community a lot of inspiration back, this is 15 plus years ago or so, on the notion of architecture and thinking about layering that way. Now, this subject that Victor is putting together, panel this morning on intelligent edge, and I think of the cloud and edge / fog as a horizontal decomposition. And all the architectures, in some sense, are there to be a little philosophical, if you will, and then to support a range of practical applications. For example, in 1948, the Shannon source channel separation is an architectural principle and very crisply stated mathematically as well. And that principle in architecture further led to the applications of digital communications. And when Minserv Bob Kahn did the TCP/IP published in '74, and that is an architectural design, and that led to the vertical applications in the internet and the web. Then the edge and fog, my biggest hope is that it will continue to be worked on by the community from industry and academia around the world and arise these architectural foundations for applications such as IoT and 5G or dispersive AIs. So I'm going to abbreviate my personal journey much shorter here. Back about a decade ago, started the Princeton Edge Lab. Back then, I got two interesting questions. One is one large Fortune 500 company told me the word edge has been, not Microsoft, has been trademarked. So I have to stop using the word Edge Lab. And the Princeton lawyer wrote something back and then never heard anything from them again. The other is that people told me, Meng, I like you and stuff, but you're on the wrong side. Everything will move away from the edge. Edge will be dumb. Have you heard of the word cloud? And distributing functions, whether it's computation, storage, or computing or control to the edge. And then back 2-3 years ago, I was the founding member of the Open Fog Consortium. Now, one could ask, why did you not like the word edge anymore after a few years? I say, well, not really. I don't particularly care about English word. And I know that, for example, Victor thinks that fog is a very vague, foggy word, and why don't we just keep using the word edge? But, if there is an industry, including Microsoft, Cisco, Intel, and quite a few others want to get together, use a term, I say that's fine with me too. And decomposing functions along this C to T continuum, cloud to things continuum. So this is sort of a wrong picture to show. But let me first tell you what is perhaps useful about it first. Now, on the one side, you've got the cloud. On the other side, you've got, well, that looks like a fog or mist or whatever you call it. Now, the interesting point is that you need both. Now, Peter Levine's provocative essay to say the death of cloud, might be exaggerating to make a point. I don't see the death of cloud. I see the rise of the edge and fog. And depending on what you want to do, what belongs to Caesar goes to Caesar, what belongs to God goes to God. And now, this picture is, however, also wrong because it is not a dichotomy. It is a continuum. There is no digital sort of boundary to say, yep, it's a choice between either and or. And furthermore, the pendulum swings back and forth. The time scale is about, 15, 20 years or so. So some argue that there's nothing new under the sun, and then we're merely swinging the pendulum every 2 decades or so, whether that's NSF or industry or PhD thesis. And perhaps it's not that cynical. I think every swing brings new ideas and driven by new context too. But it is true that the rise of the cloud, and then now there's the rise of the edge and fog, then a big believer, just like Victor myself. But I won't be surprised that 10, 15 years later at Microsoft Faculty Summit, whatever, 2034, people will say, oh, you know, this edge thing is just so like 2028. We should go centralization. We should look at economy of scale. And somebody in the audience will say, I vaguely remember when I was young, there's something called cloud. So this pendulum will keep swinging, and that is fine. There are many topics, as Victor was saying, one could talk about in edge, intelligent edge or fog, including, I think, the economic side of it is very important. How do you incentivize? The security privacy is important. But let me just focus next 10 minutes particularly on dispersive AI as one of the, in my mind, 3 main pillars of application verticals. So here you, again, want to leverage the fact that you got latency on your side. Latency in 2 ways. First, you can do edge analytics or stream mining with the live streaming of data coming to you, and you can understand it right here, right now. The other is you dare to put in some feedback control loop because you know that latency and perhaps more importantly jitter is much more under control. It's small and almost deterministic latency, so you can run control loops in cyber physical systems. Now you got to decompose the machine learning computation and control into disparate components, and then they will be working either collectively or jointly, and you can think about, you know, pre-positioning and so on. So this is about a year ago, we did a demo of one particular platform that we did at Princeton. Think of this as a MapReduce for edge or fog, and what you want to do is to look at opportunities to frame how would you decompose machine learning computations in order to map to this new substrate. Okay, so I'm going to fly through some slides here, but the typical chart you want to see, this is just a toy example last year, is to say, well, between one extreme end completely on the device, the other extreme end completely on the cloud, what happens in between? Well, there's a trade-off between what's done locally and what is coordinated, communicated globally. You want the summation to be smaller than either end, and that's a little comparison between what we did and Spark. The unique feature really is that you got in edge or fog 2 sides. On the challenging side, there is heterogeneity. Unlike the cloud, you don't have racks of servers that run on the same OS and similar hardware capabilities. You've got variability, even volatility, because unlike a rack of servers, these little things, they move perhaps, and they may not always be available. And you got constraints, bandwidth for sure, and maybe even battery constraints. But on the other hand, you also got the nice things, such as proximity, physical proximity to sensors and actuators. So the challenge is to take care of heterogeneity, variability, and constraints, and take advantage of the proximity. Now, how would you decompose a job? You know, whether it's, you know, counting words in a file, or slightly more interesting, let's say, run the least squares, for example. All right, one of the simplest things you can think of, if you run a large-scale least squares as embedded in the loop of some particular optimization for machine learning, you know how to do that by decomposing the job into parallel computation on a rack of server very, very well. But how would you decompose that job over a very different substrate, right? The edge fog substrate. So here are two toy examples to illustrate this notion of decomposing the computation over this kind of substrate. One is about drone camera work with Kangsha and Shirley in my lab. So imagine now in this particular application topic, you've got the outdoor, say, sports event like the FIFA World Cup soccer, and people have thought about using cameras over cross wires, for example. But if you use drones to capture and to transmit, what would happen, right? So here is sort of one way to look at the choices of architecture. On the one hand, you can make everything locally done, but then you lose the collaboration. You may miss some of the important scenes in the coverage, and you may have to reduce the video transmission rate out of those drones. On the other hand, you have a fully centralized version of it, and you have to make decisions centrally. Now, this cloud could be the Azure cloud way out there, or it could be even a big server on the ground. That big server to all the little drones feels like the cloud. It's just like, you know, a little rock to us may feel like a mountain to the ants. So, but you're going to suffer the round-trip time limits. The ability to coordinate in real time in response to game dynamics will be limited. So here is one particular decomposition. I'm not arguing this is the best decomposition even for this application. But you see that the drones form a little fog network among themselves. They would take care of the following functions: trajectory planning and collision avoidance. And then there is a little central coordinator for next target location optimization and deciding which drone should be doing what. So you've got 8 drones, let's say, up in the air. Which of those should help you to cover the scenes, and which should help you to relay the video streams, right? So that will be done with coordination. So there is still a controller up there, and then you've got the sensors on the balls and the players, and then you've got the, say, 8 or whatever number of drones up in the air. So the drones now, they got to decide to cover, they got to decide to transmit. And you can do other fancy things, 3D rendering and so on, if you want to do that in real time. And there is actually a trade-off between maximizing coverage and maximizing throughput. And you only got that many drones, so for each drone, should that drone help with coverage, or should that help with relaying and enhancing throughput? It turns out you can run an integer programming joint optimization, and there are some heuristics that allow you to solve it very fast, even though not truly optimally. Just a little chart to show what we did, I guess illegally on a field on Sunday mornings near Princeton. I shouldn't say that. Probably legally, flying the drones. And you look at the trade-off over there. In this particular case, it turns out that if you've got 8 drones, 4 of them to focus on coverage, 4 of them to focus on streaming is the best. Now, which is covering, which is streaming, that depends on the real-time situation. And that is actually coordinated by the cloud, if you will. So the message here is not about the application per se. We can go into that detail on another day. But to say if you want to coordinate a group of drones working with each other, certain functions can be done by themselves on the drones, and others should be done on the ground with a little server. So the second quick illustrative example is something that just we were doing it last month. It's still ongoing. It's some preliminary results here to share. It's about AR/VR, and particularly the technical problem of object placement, so that they don't block important things and don't confuse the viewer. and we want to personalize the placement challenge. The question is, where do you learn about the personal preferences, and where does the learning happen? Okay. By the way, that is actually the Princeton Edge Lab outside in the corridor over there, and those are the holograms in that experiment. So again, the main message is that there's a variety of choices in network decomposition here. During the policy learning phase, there is a user, there is an agent, and the agent will try to mimic the user and learn what is the personal preference of overlapping and foreground-background placement of the holograms. And then there is, secondly, a policy execution phase after you've gone through the learning phase. And in both phases, you can either have a little server there, or you can have the end device, in this case, the AR set, to do the computation. And what we found in this particular case is a trade-off whereby the policy is learned with the computation primarily on the little server next to these AR devices, but then in execution, the parameter choices of the learned policy is done in real time. And that's not, I guess, a surprising trade-off, but it's one that sort of worked. And this is a quick video. It's 1 minute. I'll probably skip in a few seconds. On the left-hand side will be the user. On the right-hand side is the agent. This is during the learning phase. You want to learn the policy before you execute the policy in real time. And it shows how the right-hand side agent is learning quite efficiently based on what the user is doing. It started out, if you still remember, 15 seconds ago, way off, whether the hologram should be placed in covering the real object or behind the real object, or where it should be. But within 10, 15 iterations, it learned very fast. Let me just skip to the next slide there. So one way to visualize that the learning process is, after a few demos, basically all those little dots are the decisions by the agent learning the user preference and personalized placement, and that they all aggregate to the correct place. Now, what is interesting is that if you don't use state space reduction, then even after many more rounds, you still are all over the places. On the left-hand side is you don't use state space reduction. Right-hand side is you do use it, and you can clearly see the benefits. Now, the state space reduction is carried out not on the AR themselves, but on the little server. So again, the main message there is not about AR placement. Personalization is that there's a choice of where do you carry out the learning, and one possibility is let the policy stay in the cloud, if you will, and let the actual parameter and execution stay on the end devices. So the overall question really is where, as in the horizontal decomposition, where do you place a function? And we haven't even got to the point of where do you place the data, and what is the interface among these modules over there. So my last slide is just to highlight what is perhaps obvious on why is it even interesting to explore that today. And I think of the acronym SCALE. I learned that if you want to write a winning NSF proposal, you have to come up with good acronym. Although this was refuted by Jim Grossi last night to me that that's not a necessary condition. But I guess it doesn't hurt. So S is the potential advantage on security. The less distance it traverses, more privacy is potentially protected. One could argue the other way to say, well, these little things, trusting them with more and more functions, but they are easier to hack into, and their update is not done properly. Cognition is, because you are much closer to the end user and the ambience, you have a better understanding of user-centric objective. Agility just refers to the fact that, generally speaking, you go into the cloud, the core network of LTE and so on, you go through 3GPP, and it takes forever to update and change. Whereas if you rely on the end devices, the agile development process is much faster. Latency we mentioned, that's the number one reason, as Victor also highlighted, that people think about, why do I even care and need anything other than the cloud? And efficiency is actually interesting. There's the D2D efficiency, okay, device talking to device, but then there's also the device for device, D4D efficiency, that because you have proximal distance, you can Uberize the idle resources, connectivity, computation, and so on, that are in physical proximity to each other. So SCALE, these are the reasons I think of why network decomposition horizontally closer to the user's edge fog is becoming ever so more interesting. Thanks.
Okay. So we can ask one question if there's one. We'll have hopefully have some time left for the panel. But in the meantime, if somebody wants to ask a question.
You can ask the question and I'll answer.
That's fine.
Let's move on.
We will do I have a bunch of questions for you. But we'll do it when we do the panel. All right. Thank you. Yeah. So, great pleasure to introduce Umakishore Ramachandran. He actually goes by the name Kishore. And then for those of you who are from India, I know Kishore Kumar, Kishore. Anyway, so my jokes are so flat. Okay, so anyway, so he got his PhD from University of Wisconsin-Madison. He is now a professor at Georgia Tech. His interests are in parallel distributed systems and edge. As you can see, he's been working on this space for a while. He's quite passionate about providing connectivity and services in the rural areas. I actually was there in one of the NSF workshops you had actually organized with Anish, and quite fascinating. With that, please take it away.
Well, I mean, there is this debate that that Victor started with edge versus fog. But let me ask you a quiz. How many of you know Victor's real first name? Any of you know? Among what is the name? Do you know?
Real name.
Paramveer. Paramveer is his real first name, and it means supreme hero. So and sort of lose. And you should ask him during the panel. During the panel part, ask him where he got the name, how he got the name Victor. So I think Mung and Victor, both of them gave a nice segue to what I'm going to talk about. And the title of my talk is elevating the edge to be a peer of the cloud. So that's the spiel that I'm going to talk about. And of course, I won't be standing here but for all my students who've done all the work that I'm going to sort of highlight a little bit in describing what we're doing. So I think IoT and the scale of applications that run on the IoT, all of these are things that you all are familiar with. And the key thing that Mung and Victor pointed out is that future applications on the IoT infrastructure is going to have this characteristic of sensing, processing, and actuating, and which means that latency becomes very critical in going from sensing to actuation. And cloud computing, as we know it, is great for throughput-oriented application, but not latency-sensitive applications. And there are also other considerations, regulatory considerations and backhaul bandwidth and so on. All of these may argue for moving the computations away from the cloud, and that's where fog edge computing comes in, and there is, as Mung pointed out, it's really a hierarchy of devices, all the way from the client devices to routers to servers, all the way to the cloud, right? So that's the continuum that exists in this world. And now, what I want to emphasize is the fact that today, edge computing, as we know it, it's a slave of the cloud. And you know, there are lots of very interesting platforms that have been designed. Arjman is going to talk about IoT, Azure Edge. Cisco has its own IOX platform. But all of these require that the coordination is coming from the cloud. And there's a great example that Mung already pointed out in terms of drones coordinating with one another. So that's the idea behind wanting to sort of elevate the edge to be a peer of the cloud. And today, actually, we are beholden to the cloud, because if I want to send a text message to Arjman, I have to go to the cloud and come back to him, right? And so that just doesn't seem right to us. And so vision for the future is that the edge is going to become a peer of the cloud. And there's prior art that Victor already pointed out, Cloudlets and Maui. And all of them are trying to do the following, which is sort of take computations from the client devices and launch it onto the server that is nearby. But in the limit, what we want to do is make the edge autonomous, even if it is disconnected from the cloud. And I can give lots of reasons why this might be a good thing. Because the interacting entities, if you think self-connected, connected vehicles, applications, and so on, there is a lot of things that need to happen horizontally among the edge nodes. And even more importantly, if you think about disaster recovery and things like that, we may not even have connection to the cloud. And in that case, the drone example was a great one, right? So if I have the ability to connect to, even if I have disconnections among them, if I have the ability to connect to somebody, I can actually communicate, and then eventually my information will get passed on to the others, and we can have a happy situation. So these are motivating reasons why you may want to elevate the edge to be a peer of the cloud, but there are lots of challenges making this happen. First of all, the cloud, as we know it today, is so powerful mainly because of all the infrastructure that has gone into it, right? There is programming models, storage abstractions, PubSub systems, and so on that make it a powerful development engine for rapidly prototyping applications. And now we have geo-distributed edge nodes. And we want to provide the same sort of ability for rapidly prototyping applications. And what that means is that we need powerful frameworks akin to the cloud to be available at the edge. And yesterday, Albert Greenberg was emphasizing the need for making sure that recovery is important, and which means that when you have geo-distributed data, then you have to worry about replication in a geo-distributed fashion so that you can avoid correlated failures that might happen in a particular neighborhood. And so those are important. And when you do that, then there is a latency and consistency trade-off that comes about, right? So those are things that you have to worry about. And then similar to the cloud, we want the same sort of elasticity of deploying application components rapidly, and the fact that you might have the same IoT infrastructure that is simultaneously being used by multiple applications means that you have to worry about multi-tenancy. And all of these are issues that are challenging. And in the remaining time, what I'm going to do is, lots of people are working on interesting areas related to these topics, and I'm going to give you a little bit of a sort of a bird's eye view into some of our own thoughts on addressing some of these challenges. And so I'll talk about a programming model that goes across the continuum between, in some sense, enabling applications similar to what Mung was talking about in being able to sort of share information across the edge as well as vertically with the cloud, and then how do you do geo-distributed data replication, and then also I'll motivate some example applications that might use autonomous edge. So that's the thing that I want to do in the next 10 minutes or so. But obviously, I cannot do full justice for that. and I invite you to talk to me or look at some of these publications that we have here. So first, let me talk about the geo-distributed programming model. The idea is that you have sensors that might be generating data, and the application itself may be a data flow graph that you can represent it as a data flow graph. And what you want to do is, Victor talked about what are the SLAs, right? SLAs in these kinds of applications tend to be latency, right? So given the latency properties of the application components and the interaction among them, then you can decide how to place them in the continuum, both horizontally as well as vertically in this continuum. And so that's part of what this Foglet's distributed programming model does is respecting the application properties. It places the application components in the hierarchy, in the continuum. But that's not a one-time thing, because you can have sensors moving, and if sensors move, then the fog node that used to be processing may not be the appropriate one to continue the processing, which means that you have to migrate the application component to a node that is close to where the production of data is. So that transparent state migration is part of Foglet's programming model as well. And then multi-tenancy is something that I already mentioned. And so once you migrate something to a different fog node, but you've left some breadcrumbs over here, and those breadcrumbs have to be brought over in order to continue the computation. That's part of the programming model in terms of transparently worrying about moving both the computation as well as the state of this distributed computation. That's what this Foglet's programming model gives you. And if you're interested in that, please look at this publication, and I'll be happy to talk to you also about that. The second thing that I want to mention is the second project relates to the recovery aspect of it. So when you have data that is very important, then you want to make sure that the data doesn't go away when there is failures, right? So one possibility, so the latency is also a consideration. So what we want to do is we want to replicate the data in order to worry about recovery properties. So I go ahead and replicate it in a particular way so that I can make sure that the latency that is important is preserved. But if I do this, what's going to happen is if there is a correlated failure, then all of the data is lost, right? And therefore, what I might want to do is I might want to replicate the data that are far away from the current location of where the data is being generated, so that I can have resiliency and recovery properties. But that results in poor latency, right? So there is this consistency and latency trade-off that exists. And when you think about some of these frameworks that are available in the cloud, what it'll let you do is it'll say, well, we're going to give you eventual consistency. That's all we're going to give you. And if you care about strong consistency, you look at it in the application. If there is a violation of strong consistency, you have to take corrective actions in the application. And that, to me, is not very satisfying. So one of the things that my student came up with is this idea of a context of interest. So the context of interest says that this is a context in which I want very strong guarantees in the data, meaning that I want to know that anything that I read is the most up-to-date value, right? So that's strong consistency is being provided in the context of interest. But from the point of view of avoiding correlated failures, what we're going to do is we're going to also replicate it in a faraway node, but we don't give you strong guarantees on that. So we give you eventual consistency for that. So that's the idea behind this fog store work. And again, there's only a bird's eye view of the details in that paper, but if you're interested in that, you can look at this paper. So that's the second thing, that is looking at the resiliency properties. And the third thing is the fact that you have fog resources, and Mung alluded to this, that the resources are not multiple racks. You have limited amount of resources, and you are having applications that are continuously generating data 24/7. And in that situation, what you have to worry about is how to place this data that is being generated so that you can make sure that it scales, and it also provides you low latency properties. All of these are good things that you need to do. And so that's the idea behind this data fog. And in particular, what happens is that there could be skews in the workload. Going back to the game example that you had, if there is as soon as the game ends, everybody is leaving the stadium. So there's going to result in a huge amount of activity around that area. And in that case, the edge infrastructure here is going to be oversubscribed. And so what we have in data fog is ways by which we can say, what is the data that we need for immediate query answering? So these are real-time queries can be answered by that. And older data can be moved up in the hierarchy to ultimately to the cloud. And so that's the way we think about capacity-conscious data replication. And there are details, again, on how we do that, taking both the spatio-temporal coordinates of the location of the data, and then figuring out how to sort of disperse the data in terms of replication. So details of that you can see in a publication that recently came about as well. So that's those are the examples I have of things that we're doing in the infrastructure. But I want to give you a couple of examples of applications that might use autonomous edge. And so for this, I'm going to give you an example of creating space-time trajectory of vehicles, right, on the roadways. Now, the assumption is that you know already the layout of cameras on the roadways. So in principle, it might seem like if I want to record the activity of all the vehicles all the time, it seems like a lot of data. But in practice, what is happening is every car starts its journey somewhere, ends it somewhere, right? So it's an activity. And the number of activities is bounded by, traffic conditions and, where you want to go and so on. And so that's sort of the intuition behind how we can do this, even though we want to do this continuously for all the vehicles. And so the idea is that, if a particular roadway, the cameras are attached to edge nodes, and a particular roadway, I cite a particular vehicle, and I can say this is the geo-coordinate of this vehicle, and this is the time at which I saw this vehicle here. And as soon as I know this, I can communicate to other cameras that are downstream from me, given the direction of motion of the vehicle and the layout of the cameras in the roadways, and I can tell the downstream cameras that look out for this vehicle, and I'm sending a signature of the vehicle to look for, and it is the responsibility of the downstream nodes to re-identify when that particular vehicle comes along, and so when that particular vehicle comes along, it can record that, well, I found this vehicle at geolocation G2 and a particular time T2. And once I have that, once this guy confirms that, yes, I found it, then I can actually send this partial trajectory that I have to this guy and get rid of it locally. Right? I don't have to hold it anymore. And so you can sort of aggregate all of these trajectories and keep it together. And of course, you can say, well, we may not be able to keep all the trajectories at one point, and you can do either lazy aggregation and so on. I'll talk about that in a minute. And also, as you keep on getting all of these trajectories accumulated here, you might say that some of these are old trajectories, and the recent queries are for recent tracks, in which case I can even push it into the cloud and not do that, and we can do lazy trajectory aggregation so that you can keep the footprint of storage requirement in each of the nodes reasonable. And as I said, the storage is bounded by the activities that is at a particular camera, and that's the reason that it is something that is scalable and you can do it. And again, this is only a bird's eye view of what this paper does. If you're interested, talk to me. And what we are doing right now is we are working with our campus security folks. I'm sure that this is something that most of you have experienced, that every campus has cameras. And I asked my security guy, what do you do with the camera? Oh, we have a Google map, and we can click on the camera and look at what is happening. There's no intelligence. And we ask them, what are the use cases that you're interested in? And we can actually track vehicles in real time and then record that. So that's sort of what we are doing currently with that. And another example that I wanted to give is in the context of social sensing. And what we've done is, you have multiple components in the application, and again deploy it across the continuum, and you can have network partitions. And if you have network partitions, then you can reconfigure and resume the operation, and opportunistically we can communicate when it is possible using drones or buses that carry edge nodes and so on. We can communicate with that, and this is again something that we've done before. And if you're interested, you can look at this publication. So with that, I wanted to, and there's a bunch of ongoing work, and I won't talk about that. If you're interested, I can do that because I've been asked to wrap up, and so I'll wrap up. So the final comment that I want to make is that I hope, whether it is provocative or not, but I hope I have communicated that we want to make the edge as a peer of the cloud. And Victor articulated how this is a disruption that is coming, and in order to position ourselves for the disruption, this is the thing that we want to be looking at. Okay, thank you.
Same thing. Anybody have any initial thoughts on the talk?
Yeah, Ken.
Yeah, I really like this smart highway kind of vision. The question I would ask, Satya talks about Microsoft as a company that can be trusted with privacy guarantees. I was.
Yeah.
Right. Well, anyway,
I can hear.
Privacy guarantees, security for data. I was sort of expecting between the two talks so far that somebody would start to talk a little bit about the privacy implications of edge. And of course, here you are looking at who might be driving a car and where they're driving to and who's with them. Yeah. That's very clearly in this space. Mm-hmm. So I'm just curious to know what your thoughts are about a private edge.
That's a very valid concern. And so, for instance, when I talked to the campus security folks, they said, well, are you going to publish these camera feeds on YouTube? I said, no. I'm just using it for analysis and then recording it. And we're not doing anything more with that. But absolutely right that, privacy considerations is super important. And we have a very strong group at Georgia Tech that is looking at security and privacy issues. And I hope to partner with them in terms of looking at some of those issues.
Okay, on that note, thank you very much. Ken, I'll just, one comment I'll make to your comment is that, so we've been dealing with traffic cameras quite a bit, and every city sort of deals with it differently. Some of them, for example, Seattle just puts it on the web. You can go and look at it. Anybody can. Other places like Bellevue will not put it on the web, and then we have to sort of sign some sort of agreement with them. So there is no clarity yet on how people are dealing with it because there's really no policy. Anyway, beyond that, real pleasure to introduce Arjman Samuel to you. Arjman he's a principal program manager in the Windows IoT Azure group. He is in product, but he has been in research. He was part of MSR. In fact, he and I worked together quite a bit on some projects you might remember, like Project Hawaii, and then Lab of Things, which was an IoT thing. But then he moved on to the product division, and now he thinks a lot about IoT, and he thinks about the edge, and in fact, kind of within quotes, owns the direction in which it takes. So I wanted him to share with you. He has a PhD from Purdue, so among his alumni. And he's so I wanted to share with him, ask him to share with you our existing current vision of where we are headed with all this stuff. So Ajman,
thank you, Victor. It's a pleasure to be here. Thank you, Victor, for the invitation. I've been working with a bunch of, I see very familiar faces, quite a few, and so I've been working with the community for some time. I moved off to Azure IoT, which is the Azure engineering team, responsible for IoT, about 3.5 years back. I lead the Azure IoT Edge engineering. So my team is responsible for making Edge real. And the one message I bring to this group here is that Edge is really real. There are actual customers, and I'm going to actually talk about some of those. There are actual customers who use Edge, who see the value in the Edge and the cloud, and they marry the two together. So there is a lot of momentum that we see out there, and I'm going to talk about that. So when Victor asked me I should come here, I said, what better thing to do than to bring in some real scenarios, some real actual customer use cases, and talk about some of the challenges that they see, our customers, and then really ask you, the community, to solve some of those challenges. So let's make it real. I'm going to give you a little bit of an introduction into the IoT patterns that we see. This is how we right now see. Of course, the cloud is there, and when we make a slide with a cloud, the cloud takes 75% of the space. That's by design. But edge would also come here. We look at IoT as things. Right? These are things around us. There are things here. There are things. The vehicle is a thing. Smart cities, manufacturing, machines, robotic arms. They're all things. Things do two things. They generate data, and they can be actuated. They can be controlled. Right? So these are things. Another thing, so we look at it in three ways, is insights. When these things generate data, there's a lot of insights that you can get from that data. You can understand what is the state of the machine. You can understand the state of the environment in which the machine is operating. You can also, because now you have insights, you can have some actions. You can do some actions on the machine, on the thing, or you can take actions on your end. You can adapt some processes and so on. So that's how we look at this. Data, of course, flows, as we see it today, from the things to insights in the cloud, and from there to actions, and then maybe actions come back to the cloud, to the thing. But then now, if you put an edge concept on top of it, you have, I'll skip this. You have the same thing, you have the same insights, you have the actions, and you, of course, have a cloud gateway. But what you now do here is you move some of the insights you get from data, some of the actions that you need to do, and you bring it right there on the thing. Now your thing, the robotic arm, the huge milling machine, your car, your smart city, your environment, like this conference room, they have become smart in themselves. Because those insights, which essentially is AI, machine learning, parts of those have been moved to the thing. And that's how we look at the edge, because edge and the cloud work together. Now, I won't go over some of the virtues of the cloud and some of the virtues of the edge, only to say that both of them are important in their own self. You cannot do a huge machine learning training exercise with tons of data from distributed nodes coming, and you only need the cloud to do that because of near infinite resources. But then, at the same time, if you're looking for near real-time latency, you are looking for control loops which can run reliably right next to the machine, you are not going to send calls up to the cloud and wait for them to come back, which might not be reliable. You need those insights, those AI machine learning right on that machine. Now, we can talk a lot about these virtues of the cloud and the edge and how they sit together and how they augment each other. But the way we have done, now coming to what we have done in the product, is to create a consistency between the cloud and the edge. And by consistency, we mean the consistency in programming models, consistency in the application model. What does that mean? That means that if there is a workload that you're running in the cloud, imagine a stream analytics job, which is ingesting tons of data, analyzing the data, and then coming out with some statistics. The same application model we have created for the edge, which has implications beyond just the model, which means you can actually move that same workload without any change from the cloud onto the edge, without any modification, without writing any code, all through configurations. So that is the consistency. That is how consistency between the cloud programming model and the application model and the edge programming model and application model helps us. It has implications beyond just technology. It has organizational implications, right? So now, if you do not have this consistency in the programming model, you need developers, you need people who actually program the cloud application, and then you need people who actually go in and program the edge application. But with consistency and an infrastructure which allows you to move workloads from the cloud to the edge, you do not need that. You just need cloud developers who develop their applications in the cloud, make parts of it which they want or they think or they optimize to run on the edge, and simply configure it that way. And then they can move it back. So that's really how we look at the edge. That is what Azure IoT Edge does. By the way, this is Azure IoT Edge. There's also another product, the Edge browser. This is not it. This is Azure IoT Edge, which we are talking about. OK, so now I'm going to make it a little bit real. Then I'm going to stop a little bit and go into some design principles here. This is a Rail customer that we work with. They have a mining operation. They have spread these pumps, which are spread around this very remote locations. Many of these remote locations are in the ocean. They're not even on land. And then they have one central place where they're controlling them. Network connectivity to these remote locations is very bad or very expensive. So they typically would use satellite connectivity. They can only get alerts. Otherwise, it becomes very expensive. So what they do, and also reliability of operation of this pump is extremely important. Because if it goes down, you lose money. You lose oil, which is money. So this is their world. There is a pump here, which is going up and down, similar to that one. The pump has really, it's boiled down to two values of pressure. Pressure above the plunger and pressure below the plunger. And then this on the x-axis is the position of the pump. So at all times, there is an envelope of operation for these two pressures. The minute it goes out of scope, out of that envelope, this pump fails, and this whole operation goes down. Now, obviously, there is a requirement for it to be near real time, so they need to monitor this. There's also a requirement to be predictive. You cannot wait for this envelope to be broken to take some action. You need to predict when this would happen so that it does not break down, and you can do something about this pump. Right? And you want to do it in offline. This pump could be operating in the middle of the ocean, and you do not have any connectivity to the cloud. Now, how they do it is, right now, they would have the pump. They actually have some automation, they call it. There's a gateway. There's a SCADA controller. There's an HMI right next to it. And then there's an alert. There's a supervisor sitting in the central place. There is an alert which is generated when that envelope is broken. And then the supervisor would send somebody who would start tweaking the pump, shutting it down, or doing things which they can do to mitigate that issue. So what they have now done, and of course, moving that data up to the cloud and training machine learning and all is expensive. Remember, this is satellite connectivity. So what they have done here, right next to their existing gateway and the pump controller, they have deployed Azure IoT Edge. This is right now on pumps, on mining operations. What it allows you to do is to, first of all, have some translation between the protocols that are happening, that are used. Modbus is the protocol they use, and protocols which are more IoT-enabled, like MQTT. But the second thing, most important thing, you can actually deploy machine learning right on the platform on the pump. And now you could be disconnected. And when that bad thing happens, you actually can control this pump right from there. You do not need to be connected to the cloud. Now, this is a real scenario. This is what customers use today, Azure IoT Edge today. Another one, I just have a few minutes. Another one is using drones for a number of different operations, mostly vision, video from drones. And there are a bunch of scenarios. Infrastructure inspection is one of the most popular scenario that we are seeing today. There are miles upon miles, hundreds of miles of pipeline, which is laid out there. And it's physically not possible for somebody, a technician, to go out and inspect every inch of that pipeline. So what they've started to do is fly drones over those pipelines and then take video from the pipeline. Previously, what they would do is they would collect a lot of video, bring it back to the base station, and then start analyzing. That, of course, meant they had a latency of a few hours before they would know that bad things are happening there. So they're using, and I'm going to go into this scenario a little bit more. Smart agriculture, there's a lot of work that has happened just to understand how the agriculture operation is happening. Drones are used there. And of course, our favorite scenario, which we like to debate a lot about, is surveillance. And there's a lot of scenarios where legitimately you could use drones there. So Azure IoT Edge can actually sit on top of a drone. The drone that it sits on, we have a partnership with DJI, which is a major, one of the world's biggest drone manufacturer. We work with them. They put Azure IoT Edge right on top of the drone. And then through connectivity with the cloud, you can move your machine learning onto that drone. Then these cheaper drones, this is about $1,000. That's about $15,000. These cheaper drones, you actually can set up a base station. They do not have sufficient compute, more importantly, battery to support edge compute. So you can actually deploy it on a base station, and then within that environment, you can do AI and ML and so on. So these two are actually there. Soon they'll have an SDK, DJI will, where you can actually, developers can develop using Azure IoT Edge to deploy things onto the drones. How does the whole thing work? You have a video camera, which is a drone video camera. We have IoT Edge device on the drone. This is a little NVIDIA chip that sits there. On top of it, of course, in the cloud, we have IoT Hub. And you have a bunch of your smarts, AI and ML, in the cloud. What you do is you containerize them. We use Docker container technology. You host it in the cloud in a container repo. You could use Azure Container Registry or Docker repo. And then you could move containers there. You build a manifest. You move it onto the drone. The manifest knows what are the different components you need to move down onto the drone. And then Azure IoT Edge runtime starts moving those containers onto that platform. And then you could be disconnected as long as you have the smarts which are required for the drone to fly. You could be connected again. You could be doing it at scale. So the whole value prop here is to actually allow you to not deploy one drone, but to deploy thousands upon thousands of drones and keep it updatable. You have a new machine learning model, which you have retrained based on data that you got. Now you want to update your drone with a new machine learning model. All you do is do a second version of this container, push it up there, update the manifest, and now you get the new version. So here are some design principles that we follow. Of course, security is one of the most important ones that are required for edge computing, given the devices out there. We have invested quite a lot. We have created some partnerships, quite a few partnerships with silicon vendors. We have already announced NXP, Microchip. They actually create the right security frameworks for edge to work. We also have, all of this is cloud managed, while it can be disconnected, but to bootstrap the device, you need cloud management, but it is done at scale. So we can manage millions of IoT edge devices which are deployed out there from the cloud. We can provision them with zero touch. We can also move configurations down onto those devices with zero touch. Cross-platform IoT edge devices, the ones which sat on top of the drones, are Windows, can be Linux, multiple versions of Linux. As long as the OS supports containers, it can actually deploy Azure IoT Edge. Portable, we have a full dev experience, CI/CD pipeline, and so on for this. And then extensible. It's not only Azure services that you deploy there, not only Azure machine learning, not only Azure AI, and so on. It could be your own code. It could be your own smart AI that you want to deploy onto the edge. You simply package it as a container, put it somewhere, and then it can be deployed. In fact, can I finish, and then I'll come to the question. In fact, what we have done here, we have created a marketplace for all of these modules. We call them modules, all of these containers to be discoverable from where you can deploy onto the edge. And I'll briefly touch on that. So in terms of hardware, anywhere from this interactive tier is something similar to a Raspberry Pi, which can host Linux in containers, all the way to accelerated tiers. These are FPGA-enabled, GPU-accelerated hardware. IoT Edge can exist there. We are open source. Azure IoT Edge is on GitHub. MIT license, totally open source. You can pick it up and do whatever you want to do with it. It's Moby-based, so Docker is based on Moby technology, and that's what it is based on. We have a marketplace where you can actually go in and buy these or get these modules. Security, intelligence, we have a bunch of tooling, different languages. We have 5 languages in which you can actually write these modules, C, C#, Java, Node, Python, and you can actually deploy in any of these languages. Since I have a couple of more minutes, scale is one of the big challenges that we face today. Scale of deployment. These mining operations do not work in onesies, twosies. They work in thousands to millions, right? And they ask for that kind of scale. And not just scale of deployment, but scale of management, scale of state management, scale of monitoring. All of that has to be always at least 1 million devices that they think of. So that's something that we have been thinking a lot about. We provide zero touch for millions of devices today. There's a lot to be done there. Supply chain has to come up. Silicon has to evolve, and all of that is happening. Adapting workloads based on hardware, network cost. So all edge devices would not be the same. They would be different, small, big. And so you have to upload, you have to have the right modules which go there. And how do you do that? There's an optimization problem in there, which together with Victor's team, we are investigating. There's a lot of work that we are doing on security. When you move workloads, cloud workloads to edge devices deployed out there, you have to be very careful with that. You have to have the right silicon. You have to have the right models. Operations, I talked about that, but one thing that has come up again and again, edge devices, when they are deployed even on these mining operations, are not single vendor. They're never single vendor. There is the owner of the operation. There is the owner of the pump, which is different, and it's leased to them. There is the oil, the entity which has interest in the oil, who's selling that oil to somebody. All of them need a slice of their data and a slice of that operation. And all of that has to be part of our access control models, part of how we deploy and the policies and so on. So just a quick overview of the research challenges we see. Azure IoT Edge is open source, GitHub. Go and play with it and hopefully contribute to it as well.
Thank you very much, Ajman.
Thank you.
So there was a question. In the meantime, Lynn, can you please set up?
So this looks like incredibly cool stuff. So I'm kind of curious about, you mentioned security and a couple of the challenging issues there, and I don't want to ask a long involved question about that, but the question is, is there a simple mental model for how to think about security as I extend to the edge? And do I have to trust the hardware? Do I have to trust some other third party? Is Microsoft going to have some sea of devices that can be secured or whatever?
Sure. So I didn't mention I also lead security for Azure IoT. So I can actually talk at length. Maybe later on we can do that. But just to talk about quickly, there is trust that is in the cloud, which obviously you trust more because we make sure that it is trusted. What we do is we try to take that trust and bring it to the device. How we do it is through device identity and attestation. We identify the device through hardware means, so TPM and such, and then we build trust with attestation of firmware and software that runs on top of it. And this part of it is not only Microsoft doing it. We have to have silicon, firmware manufacturers, OEMs who contribute to it. To enable that, we have a certification program. So we certify IoT edge devices which conform to this whole building of trust mechanism. Right? So it's not any device. If you want to be really secure, you go and get the certified device to do that.
All right. So I know there are more. I think we'll see how it goes. So thank you so much again, Arjman. All right. So now, so you're getting, hopefully you're getting a sense of different things and different problems that exist, and your mind's already churning and in terms of where we are in the product world, where research is, and where we want to be. The next speaker is a rock star, really is. In fact, the speaker next to him, he's not going to speak, is also a rock star. He's a 2018 rock star from Sigmobile, and you are?
2014.
2014 rock star from us. And I'm not making it up. This is the Rising Star Award for those of you who are in other SIGs who don't follow the rock star thing. So anyway. Right. And Lynn is a professor at Rice University. He graduated from Princeton. So there you go, another one of your, yeah. And I've known Lynn for a very long time, and he's great. That's it.
Thank you, thank you, thank you. That's a good summary. Thank you very much, Victor, for the invitation. It's my pleasure to talk about a vision Kyle and I shared. It's a really joint work, although I'm the one speaking. You can tell who am I based on here, right? And Victor also gave us the feedback about this. We're going to switch gears about, we're going to talk about 5G and try to point the link between 5G and edge and what edge can do for 5G. And truly, we think it's 5G needs edge. So the question, are we ready, right? I think 5G is coming, right? This is a once-a-decade opportunity for us. I like to joke, like my tenure, my full professorship, all based on 3G and 4G, right? I did a PhD, smartphone takeoff during the era of 4G. Mobisys took off of the conference, flagship conference for Sigma Mobile. A lot of things happened. Here is Microsoft. I would say Apple and Google seized the opportunity of 4G and had Android and iPhone really big. I'm sorry, Microsoft, Windows Phone missed the opportunity, but 5G is here. What will Microsoft do? What can we do, right? So the takeaway is there's 4 takeaways. We think we need software in the 5G network infrastructure because software is fast and we should use net software to eat everything, right? We should, for software to actually eat the telecom infrastructure, we have to rethink of software's, the whole software stack for efficiency and availability. And number 3, to use edge for telecom infrastructure, and we have to rethink of its architecture. We have to think of a disaggregated architecture. We have to think of how to integrate accelerators into the edge cloud. And number 4, I think it's once you have 5G, have the edge cloud there, it's a great opportunity to think of what the novel, new things you can do previously not possible when adding services. And I think I'm a computer engineer, so I like to summarize, and when I summarize the history of telecom, I like to think of the entire history of telecom is using hardware, more and more hardware to solve the spectrum problem, because hardware is cheap and getting cheaper, even post more and more, right? But in contrast, spectrum is scarce, and it's determined by physics. You're never getting more spectrum, right? Even FCC could open up more, but still, they're predetermined by physics. Wireless communication is about throwing resources, more computation, so that you can use spectrum more efficiently. And here showed is basically massive MIMO, one of the key technology for 5G. You could use a lot of antenna, a lot of parallel processing power on the base station so that you can serve multiple clients at the same time to increase spectrum efficiency proportionally. And if you look at 5G essentially is about using more hardware and to improve spectrum efficiency and to reduce the latency, right? Think of a massive MIMO as an example. Think about small cell density deployment. It's about more APs, more infrastructure, and think about millimeter wave radios. It's about more hardware, right? So my team actually is I would say, we're the first one to build actually the first massive research prototype a number of years ago. And that set us on the track to actually experience the pain of the entire telecom industry. Is over the past 7-5 years, we have built 3 generations of the Argos massive MIMO prototype. This is the first generation. And this is the latest one we deployed on campus after $1 million from NSF. It's the CRI grant with the newest base station like this. This is just newly deployed on top of roof as a research prototype. This is a world perhaps first deployed massive MIMO network testbed. And the good news we got, for those of you who like to use it, we just got an award from NSF. It's going to make this part of the commuter infrastructure. It will be deployed on the campus of the University of Utah, so as an open access testbed. But this sounds like a success story, but I think this is a failure story to me, right? Looking back, it took 7 years, 3 generations, 1 entire PhD, and we didn't innovate any algorithm, any new things, right? Basically, we did all 3 generations is update the FPGA. When bigger FPGA become available, more from Xilinx, we need to upgrade the board, and it took 7 years. So this kind of exemplify the pain of the telecom infrastructure. Specialized hardware, special equipment lead to slow innovation, expensive equipment, and very high cost of ownership and capital investment expenditure. If you look at the history to 1G, 2G, 5G, 4G, 3, each G take 10 years at least. Can we use software to make this process faster? Can we softwareize the telecom infrastructure, bring in innovation, what we have seen in the mobile cloud area to telecom infrastructure. That's our position today, right? The 5G infrastructure needs a software approach, and it's a great opportunity for Microsoft, for us researchers working on the software systems. And I think the two lessons we learned, I think it's from our experience building the massive MIMO base station, and also I think it's also kind of the lessons from the past 4G, this is 3G deployment, is number one is software innovations faster. We talk about it. We should maximize the software and minimize the use of specialized equipment. And number two, I think resource integration is bad. I will talk about this points. By resource integration, if you look at today's base station, look at our Argus base station prototype is a good example, is all the resources, RF actuator and hardware and software, both are integrated in base station. And in this particular case, they're integrating this board, which has FPGA and memory and software stack, everything in it, right? So that need to very slow technology evolution, because FPGA, actuator, software, and RF, they have a different pace of innovation, right? Some are faster, but because you put in the same board, in the same base station, you have to wait for the slowest one to update the whole thing, right? It's impossible inter-cell resource sharing, because each base station serve just the user in the cell, right? When you don't have many users, but your computation resource there is sitting there idle. And number three is when you try to coordinate two cells, two base stations, it's become difficult because you have to need very high throughput between them to coordinate. What we argue is we need to have disaggregated radio access, almost like what's happening in data center. We need to have resource disaggregation data centers. We need base station should only have RF, perhaps ADC DA, and with IQ samples to a heterogeneous disaggregated local data center where the computation will be acceleration or software. And with this architecture, we will be able to independently evolve each of this technology, and we'll be able to consolidate resource between many cells. And we should be able to very easily deploy value-adding services of software just to the edge, right? For example, localization service. Now it could be, in the past, you have to change each base station. Now you can just put on a piece of software in the edge. If you want to do, for example, this is you could also use the software to handle density deployment. This is an example from Kyle's group. And you could have very cheap access point density deployment and a link to edge server in software. And you can handle the mobility and reliability in software, and also can leverage the property of the propagation of the channel to enhance the throughput. This actually is Kyle deployed this in Princeton campus. That's a computer science building campus. The white blocks are the access points deployed there, very cheap, and they're linked to a server, which runs a software that handle the link is switching between these different access points to deal with the path fading problem. And the blue is downlink, and then the green uplink, and everything is done in software. Okay. Another example. This is a work Victor collaborated with Kyle and Giovanni Paul from Paris, and this is how can you use your phone to help each other recognize where are the available parking space in a busy city, right? You just use your phone, the phone running real-time cars, localization, recognition algorithm, and some of the logic will run in the edge. And the users, they could share information, help each other find where are parking over the parking space. This also goes back something when I was on sabbatical with Victor Group 6 years ago now. Wow, time flies. 6 years ago, when a lot of wearable devices showed up, like Google Glass, we had this vision of continuous mobile vision, that the cloud, your computer, personal computer, always see what you see, right? Therefore, they can do a lot of interesting for you. We actually bought a bunch of Google Glass and run software there, and the effect is it's going to kill the battery in 20 minutes, and also it's going to burn your skin quickly. And but I think with the edge cloud, with the short latency promised by 5G, and you can really move a lot of computation to the edge, so that your wearable could stay cool and friendly. So I think important challenges for doing things in software. This is move things to the baseband processing to the edge. I think this we have heard the story of Cloud Run, C-Run years ago, but that didn't take off. One of the key challenges is, according to my insider information from Huawei, is the efficiency is terrible running baseband processing software in the edge server. And reliability is also questionable compared to traditional specialized equipment. So to really to enable software to eat the 5G infrastructure, I think it's very important to rethink about software stack and how can make it efficient, how to make it as available as like a big public cloud. Right? So one of the solutions to solve the efficiency is your accelerator. For example, cows go by showed by using GPUs, you actually can improve the efficiency by many folds, 20 times, for example. And this could be network integrated into the edge data center, and to enable you to update your accelerator and CPUs independently. Right. Now, I think to rethink the software stack for efficient availability, I'm going to say something very controversial. I think there's a lot of low-hanging fruit, but I think after you have optimized for everything, then you realize the Linux operating system, I haven't studied Windows kernel, so I cannot say about Windows, but Linux operating system actually would eventually become the bottleneck for efficiency and availability. If we would like to cloudify the telecom infrastructure, we need a new software stack, we need a new kernel. The reason is very simple, because it uses unsafe language, therefore there's a lot of runtime checks, so you wouldn't be able to run software efficiently. And number two, Linux operating system have very weak modularization. To update one module, you often have to hold the whole system, right? So I like this graph. We basically, also from Microsoft, Galen Hunt and Jim Lawrence a number of years ago, they had this project called Singularity. Singularity vision is to say, hey, make sure the correctness of software at the compile time, implementation time. Don't do it at runtime. Linux and C, basically, you enforce correctness runtime, which is like the airport security check, right? Every time you go to an airport, they just scan you, right? We really need a software stack like TSA Pray. Basically, you check the correctness offline, statically, and when they run, just run fast, let it run. Right, so that's one effort going on in my group. We're building a new operating system, runtime composite operating system using Rust, intended for use in the edge. Again, let me summarize. I think I convinced you 5G is really opportunity for software people. It's a software play, and there's a lot of opportunity for the edge cloud there to support the 5G infrastructure. Okay, thank you.
Thank you very much. Okay. Well, first, thank you very much for great presentations and giving your own point of view on this. I was sort of, when Mang presented, he had a slide, you had a slide in there where you sort of talked about some of the assumptions, and one of the assumptions you had was battery and energy. But then as you look at some of the other talks, except for the drone case, that was not the assumption. So what that means is, and you will also encounter this, which is, people will have different definitions of edge, what it is, or edge clouds, or even fog or cloudlets, and we'll have very different definitions of it. And that just sort of shows that we are kind of sort of evolving and trying to make it more crisper in our own head as to what it is. Now, one thing that you guys did not talk about, which I see as emerging very recently, in fact, Microsoft announced something, and then I heard Google announce something, and I believe Amazon also has that, is specialized hardware for the edge itself. So what I have in mind, what I'm thinking about, is this notion of having a PC or a server rack with some specialized hardware. What are your initial thoughts on that specialized hardware existence? Anybody can take that, and you guys have the mic, right?
Yes, I think the specialized hardware is. I think it's about how it should be part of architecture. I think it's. I think the SmartNIC, the dog burgers using FPGA in the data center is a good example. The FPGA is not the whole thing, but part of the architecture. I think in the 5G infrastructure, when you try to softwareize codified, I think it's using FPGA you should bring FPGA as part of architecture instead of have everything on FPGA. You specialize hardware. I think you should selectively use them for the critical paths, for example, the data plane.
So let me, I'll let you speak, Kyle, and the rest of you too. So just to sort of be even more crisp, there's a lot of thoughts about machine learning on the edge. Like there's a debate on how much you can do in the edge, how much you can do cloud. You shrink the models to put it on the edge. But when you have specialized hardware, that tends to open up more avenues to do more stuff. And so that's kind of what I'm saying. So for 5G, I understand that. But any other thoughts?
Can I take that?
Yeah, please.
So I think there's a place for both. There's a place for general purpose hardware, CPU-based compute, as well as very specialized hardware like GPU acceleration or FPGA acceleration. And in the edge world, again, workloads tend to be both. But for workloads like machine learning and very specialized AI, yes, FPGA is a venue. GPUs are a venue. We already have Brainwave, which we announced a few months back, which allows you to download your ML into your hardware, which has FPGA, and then it fully uses the FPGA. So that's Brainwave. It's already announced. We also have a bunch of collaborations on cameras with GPUs. Qualcomm is one of our partners, where we enable the GPUs to be used on that camera for acceleration of frame detection and so on. And that's all IoT Edge doing that. So yes, there's a place for both, but I think in the end game, it won't be any one of those. I think it will always be a combination of the two.
So since my core research is really in optimization algorithms, so I hasten to comment too much on hardware, but I just want to quickly point out two things. One is that I think it was Ken who asked about security, and I have this uninformed bias opinion that on the edge of fog, the hardware-based security probably is a much likely route for trust. Now, as to the second point is Microsoft is moving fast, and so are some of the other companies. So some of these are not technologically driven per se, but really is trying to tip the balance of power in the industry food chain. And sometimes having specialized hardware may or may not be actually of use in a particular domain, but a lot of companies certainly feel that if I don't do something along those lines, I'll be left in the dust as the balance of power shifts with the rise of the edge.
So also,
very interesting observation, and there's some truth to that.
To add to all of this, you think about wireless networks, and we are seeing the limiting factor, especially with the 5G technology, 60 gigahertz, small cells, massive MIMO especially. Limiting factor is shifting from what we do in the wireless design to the computational power and behind the wireless algorithms. And so computation is becoming the bottleneck. And specialized hardware is allowing us to be more parallel in the processing that we do behind the wireless algorithms for the edge. And so it's going to play a huge role, GPUs and FPGAs in base stations and on the edge.
So I want to add that.
So let me add to this point. I mean, in our own experience, in our lab, similar to what you were saying about the Azure Edge, we built a cluster of Raspberry Pis to serve as a fog node. And as I mentioned in my talk, we want to create the ecosystem at the edge, similar to the cloud. So we brought pub subsystems like Kafka and storage system like Cassandra to run on the edge. And then we were doing this camera processing that I was talking about, and the limitation is how many cameras, frames per second that you can do. Even if you have a cluster of Raspberry Pis, we are limited by that. And so at that point, you have to include some additional capabilities like NVIDIA boards in order to do some of the image processing faster. So there is an opportunity to sort of integrate. For the mundane stuff, you can use off-the-shelf components, but for more specialized processing, you may need to incorporate additional smarts in it.
Great.
So I want to add that I think specialized hardware is all about non-recurring engineering cost, right? You need a massive quantity of a market to amortize the non-recurring engineering costs. You need that big lumber, right, to amortize that. So otherwise, it doesn't make sense economical to make an ASIC just for for machine learning.
So you're saying, so your point is that you need a lot of edges for specialized hardware to take off.
Right. They use the same hardware. The same hardware will require a lot of deployments, a lot of devices to use them to amortize the network engine. Right?
Yeah.
FPGAs, GPUs.
Right.
Right. So I would have a
like
follow-up question on, but I will not. And the follow-up question would be something like, what kind of hardware would you bet on? But let's table that because I have a bunch of other things to ask. So, so I want to ask. Kishore set up another vision, right? So he sort of said, or a vision, which was about like cloud being, or edge being parallel to the cloud. And many of you actually articulated a different vision where the cloud and edge play together. Cloud is absolutely necessary and the edge is necessary. So for those of you who did not claim the vision that Kishore did, I want to see what your reaction was to what he was saying. Please.
I like the vision a lot. There is a distinction between the edge using the cloud versus the edge becoming the cloud or replacing some of what the cloud can do. And I want to highlight that sometimes the word cloud can also, like the word edge and fog, be used in multiple ways. So one particular example is, this is regarding a particular startup that I founded called DataMe, and details doesn't matter, but it turns out that when we try to do billing and the byte counting in an LTE network, if you do it in the core network, which can be drawn with a big cloud, occupying 75% of the slide, then A is expensive, B is privacy intruding, and C is kind of slow. Like 24 hours later, the network operator can tell you something about the pricing policies. So if you want to innovate pricing, you've got to first innovate doing that in the edge, like among the end user devices. Maybe, for example, to detect the peak valley condition of an LTE cell, turns out that you don't need to rely on the LTE core. You can actually do some of that on the devices. But the point is, that actually is echoing Kishore's point, right? That is an example of the edge becoming the cloud, not just using the cloud. However, to do that really efficiently, you can't rely 100% in that startup's case on all the devices doing them autonomously. So we actually had a little controller in the other kind of cloud, in the Azure or Amazon, if that doesn't trigger, you know, some fire alarm here. In that cloud, it's not the LTE core cloud. It's a different kind of cloud. And put a little provisioned controller to enhance the efficiency coordinating the mobile devices. So we still want that kind of cloud, even though this is literally killing a function and replacing it of another cloud. So this particular example, this worked out that we have 60 million users in the world using this product right now. But it both echoes the point that edge can replace cloud or be on equal footing, but also highlights the point that it still doesn't hurt to have some form of cloud.
Sure. Yeah, I would disagree a little bit there. You still need a cloud, the cloud, and I'll tell you what are the scenarios in which you actually need a cloud to bootstrap your edge devices, and this is how we do that. One of them is security, or more precisely, trust. Right? When you have all of your devices, which now you call your cloud, distributed, how do you build trust amongst them? And where is your center of trust? Right? So cloud gives you a convenient way of saying, okay, trust is in the cloud, and from there I can actually start trusting software, do attestations, trust hardware, and then I can start deploying these. So essentially there's a master-slave relationship in terms of trust there. That's one. Second is availability or high availability scenarios, which require coordination amongst distributed compute nodes. And one way, of course, is that each one of those nodes talk to each other, do election, and so on. But then you still need some way of understanding if these nodes are distributed widely, and how do you coordinate between them. So you need some place where they all come down to, and cloud would allow you to do that. So, and of course, the final thing here is how would you manage a very large data set? You could do that. You could create little nodes with Raspberry Pis, put little data on all of them and start coordinating, but it's a huge data problem then. Rather than going to the cloud, putting all your data in there and doing machine learning there, because you have almost infinite compute and resources there, and then moving your inference down to those edge nodes. So while I do see edge becoming more and more powerful, edge supporting so many more scenarios, but I still see there's a place for the cloud in there for security.
Yeah, I'd like to add something that has not been said by anybody yet. So if you go to first principles of cloud, part of it was that I sell shoes. I don't want my IT department. I want somebody else to take care of the whole thing. And I'll just write you a check, and all your machines, all the upgrades, all the other good stuff just happens somewhere else. And I don't have to, I can go sell shoes. And I think, so that's kind of like, it was one of the big value proposition for cloud. You didn't have to worry about hardware, you didn't worry about software, you didn't have to worry about management. It was a computing resource available to you. So I think in the edge world, you're going to need something like that. You can't, if you build a system which is completely separate from that, you are actually back to the old world where you're now back to you having an old IT department, back to having all these guys who are trying to deal with the edge cloud.
Can I?
Please do.
So
yeah.
I just want to be sure that I wasn't articulating that we get rid of the cloud. All I was saying was that we want to put the edge on an equal footing with the cloud, and there are applications in which that is super important. So if you think about connected vehicles, the latency properties suggest that you want these kind of communication to happen very quickly between the edge. On the other hand, if all that I'm interested in is knowing the density of cars in a particular roadway, I can send all this information to the cloud, process it offline, no problem with that, right? So in that sense, there's a coexistence that is super important, and I think cloud can play a huge role, exactly what Arjun was saying, in terms of management of the resources. For instance, in the social sensing application, if partitions happen, recognizing that partitions happen and re-architecting the application components so that you can continue the application is something that you would expect to happen in a central fashion from the cloud. So management functions are super important, trust is super important, and those are things that is going to come from there. And one more thing I want to add, which is sort of you alluded to at the beginning when you introduced me, in affluent communities, we take cloud for granted. Everything that we do relies on the cloud in affluent communities. And, Georgia Tech is located in Midtown, Georgia, Midtown Atlanta, and just, across the north side drive, there is an impoverished area, economically depressed area, and aspirations of the people are exactly the same as aspirations of people in affluent communities, but they don't have access to the information and services that we take for granted. And so one of the things that I'm hoping is that, this edge infrastructure can actually help in sort of addressing the digital divide better than what cloud is doing today.
Yeah, that's great. I'm going to ask you one last question. We'll be 5 minutes over because we started 5 minutes late. You guys should think if you want to ask some questions while I'm asking this particular question. So I think to Kyle and Len, you guys, I thought that was that's a pretty compelling story that you put together. I also agree that the rate of innovation in 5G and telco has been substandard. It is way less than what the IT does, and part of it is because they're calcified because of the architectures that they have created and are not able to. They're very worried about switching anything. And so the vision that you are painting here is that get out of the hardware business to the extent possible, do everything in software. The thing you didn't say, but it's implied in there is, take the IP network, don't use your own stack, and you can do pretty much everything you want to do after that. And then you painted that edge is important. So the question to you, and actually to others is, as you think about the talk that these guys gave, what is your opinion about that talk? But the question to you is, this sort of thing was tried in China, right? There was this big project called CRAN, Cloud RAN, where the ideas were same. They said they didn't want to be held responsible for all these standards that take forever to do. So let's take all the signals, bring it back to the cloud, we'll compute it, and we give it back, and it's all. But that was about several years ago. I don't know what the state now is. What did they do wrong, if at all, versus what you're saying now?
I think the key problem, that's a great question. I actually kind of touched on CRAN while we were giving a talk. I think CRAN is the right direction. centralized, share, consolidated, and using software. But I think as far as I understand from people I know from Huawei, the equipment vendor, is the electricity bill is just too high when you run things in software. The base station today, a macro cell base station could already cost you $250,000 a year just for electricity bill. But now if you move the processing to software, and that's just tenfold of electricity use. So I think if we would like to cloudify the telecom infrastructure, we have to make the software efficiency get close to specialized equipment. That has multiple routes. For example, rethink the software stack, use actuators as part of architecture. I think that, yeah, we have to solve this hard problem.
I see. But you think that, so you're saying we have to solve, but there is no, I was thinking of, is there some magic to the new architectural thinking of saying we got to have the edge here and that will make the problem. So if it's the electricity problem, it'll actually be less because we are doing this.
I think, so let me try to respond. This is a hard question to answer, but let me try to respond to one source of magic is how we can co-design classical network protocols that we know with this new architecture, this new edge cloud architecture, co-design of the protocols. So for example, co-designing the Wi-Fi reliable transmission with multiple roadside hotspots, co-designing in the cellular context, in the 5G context, co-designing the base station LTE protocols with the new architecture. That's going to be the interesting intellectual challenges going forward.
Great. Did you guys have a comment or should we move on?
I'll just make a meta comment, not just specific to this question. What I see right now is a huge gap or lack of standards for edge computing generally. I know OpenFog is doing a lot there, whatever you call that, but the name itself. But there is a lot of need for different communities to come together and work on standards. And there are disparate standards. The security standards we use today were developed and designed for IT world, and now we're trying to put them into the IoT world. The whole container standardization was not done for IoT devices. It was done for server class devices, and we are trying to simply reuse that too. So there's an opportunity where, not just in this area, but all of the edge, the whole stack, where standardization could help a lot.
Okay, great. Is there a question from the audience? Yeah.
So I thought this was a really interesting panel. I guess my question relates to Azure IoT more than the rest, although welcome answers from anybody. So personally, I believe that we're going to have an edge that's mostly connected to the cloud, but that because of these real-time and hardware pressures, that the OS and system infrastructure has to change, because the traditional Azure is a very long stack from external events to back-end processing back to the front. We heard comments about that. Here we're talking about strongly consistent real-time reactions with hardware in the loop, which are all things that really are quite different from Al's vision of what Azure's fabric looks like. The hardware, for example, in the loop is not really accessible to me as a client using Azure. It's accessible to me through Azure services. And they're mostly using that kind of hardware somewhere deeper in the cloud. So I'm wondering how you see the Azure IoT evolving kind of as an operating system or as a software ecosystem that enables the customer to directly leverage, for example, RDMA into FPGA clusters. These are things which Microsoft talks about all the time, but there's no doubt that they are not viewed as end-user technologies right now.
I agree with that. I mean, there's, again, gaps. We're talking about some of the gaps. And you're right. In the data center, there's multiple levels of indirection before you hit the hardware. So there are layers upon layers, and our customers really get the highest level of layer if they want, and they can go down. For the edge, we have tried to create some layering there, which is more friendly to the developer and hence the user, which is through containers, right? So if we can move containers around, which tends to be contained in that way, we can give some level of abstraction on top of hardware. But still, you're right. At the end of the day, the customer who's deploying an edge device has to be involved in the maintenance of the hardware, the management of the operating system, and anything above that, including the container management system. So I believe these are early days. They would still, you're right, there probably is an opportunity to create an operating system all up which abstracts all of that for our developer as well as the user. But I don't think we are there right now.
Yeah, I was going to just make a little comment again that just stay tuned. So the things you bring up are actually on our mind as well. And what you see today is as I say, is a very early version of where we are and where we want to go. So anyway, I have been asked to cut this off, so we will. Once again, let's thank our panelists and our speakers. And thank you very much for attending, and let's the conversations continue. Thank you very much.